So here's something worth thinking about as you settle in tonight. Right now, wherever you are, whatever time your clock says, that number, that specific hour, that specific minute, is essentially a fiction. I don't mean it's wrong, exactly. I mean that the whole system we use to carve up the day, to say it's 9:15 or it's midnight, that system is a human invention, layered on top of something much older and stranger and harder to pin down than you might expect. Time itself, whatever it actually is, doesn't come with labels. It doesn't come with hours. It doesn't tick. We made it tick. And the story of how we did that, how we went from watching shadows move across the ground to synchronizing atomic clocks accurate to a billionth of a second, that story is one of the most quietly fascinating things in all of engineering and science. And it's a perfect thing to unspool slowly, here in the dark, because time is the one subject where going slowly actually helps you understand it better. Let's start where everyone starts, the sun. If you'd been born 10,000 years ago, your experience of time would have been almost entirely about light and dark. The sun comes up, the sun goes down. That's a day. You don't need anyone to explain that to you. Your body already knows it. There's a clock built into your biology, your circadian rhythm, that roughly tracks the cycle of light and darkness. It's not perfect. Your internal clock actually runs a little longer than 24 hours, which is why, if you put someone in a cave with no light cues at all, their sleep cycle starts to drift. But it's close enough. For thousands and thousands of years, that was all anyone needed. Day, night, day again. The seasons rolling through. The moon waxing and waning, giving you a rough sense of months. But here's the thing. Even very early on, people wanted more precision than just daytime and nighttime. If you're coordinating a hunt, if you're organizing labor, if you're timing the irrigation of fields, you need to be able to say something more specific than when the sun is high. You need to divide the day into pieces. The Egyptians were probably the first civilization to do this in a way we'd recognize. Sometime around 1500 BCE, maybe earlier, they were using sundials, or more precisely, shadow clocks. The simplest version is just a stick in the ground. You watch the shadow move, and you mark positions along the ground to indicate different times of day. They divided the daylight period into 12 parts and the nighttime into 12 parts, giving you 24 divisions total. And that's where our 24-hour day comes from. It's Egyptian. It's 3,500 years old. Think about that. We still structure every single day of our lives around a choice the Egyptians made, probably because they liked the number 12. 12 was a big deal in Egyptian mathematics and culture. They counted in a base 12 system using the joints of their fingers, 3 joints on each of 4 fingers, thumb doing the counting. 12 shows up everywhere in ancient systems. 12 months, 12 zodiac signs, 12 hours. But here's what's a little strange about the Egyptian system, and this is something most people don't realize. Their hours weren't all the same length. A daylight hour in summer, when the days are long, was literally longer than a daylight hour in winter. They divided whatever daylight they had into 12 equal parts, so the hours stretched and compressed with the seasons. We call these temporal hours, or seasonal hours, and they were the standard way of thinking about time across most of the ancient world. Not just Egypt, but Greece, Rome, and later the Islamic world and medieval Europe too. For over 2,000 years, an hour wasn't a fixed thing. It was flexible. It breathed with the seasons. A summer hour in Rome might be about 75 of our modern minutes, while a winter hour might be only about 45. And nobody thought this was weird, because why would they? The point of hours was to divide the day into useful chunks, and the day was defined by sunlight. If there was more sunlight, each chunk was bigger. It made intuitive sense. Now, you might be lying there thinking, okay, but that must have been a nightmare for anything requiring precision. And you'd be right. But precision, in the way we think about it, wasn't really the goal. Life moved at a different pace. You didn't need to synchronize your activities down to the minute with someone across town, let alone across the country. The local sundial, the local church bell, the local call to prayer. That was enough. Everyone in your village or your city was on roughly the same time because everyone was looking at the same sun. And speaking of sundials, let's talk about how they actually work for a second, because it's cleverer than just stick in the ground. A proper sundial, the kind the Greeks and Romans refined, uses a gnomon, which is the part that casts the shadow. And here's the key insight. If you angle the gnomon so that it points toward the celestial pole, toward Polaris, if you're in the northern hemisphere, then the shadow it casts will move at a consistent rate across the dial face because it's aligned with the Earth's axis of rotation. The Earth rotates around that axis once per day, so the shadow sweeps around like a clock hand. In fact, that's exactly why clock hands move the way they do. Clockwise motion is the direction a shadow moves on a sundial in the northern hemisphere. If clocks had been invented in the southern hemisphere, they might very well run the other direction. But sundials have an obvious problem. Clouds, night, rain. You can't tell time with a shadow if there's no sun. So people developed other ways to measure the passage of time, what we'd call clocks, though that word wouldn't exist for centuries. Water clocks were among the earliest. The Greeks called them clepsydra, which means water thief, which is a beautiful name when you think about it. The basic idea is simple. You have a container with a small hole in it, and water drips out at a roughly constant rate. You mark the water level on the side of the container, and as the level drops, you can read off how much time has passed. Or you do it the other way. Water drips into a container, and the rising level tells you the time. The Egyptians had water clocks too, some dating back to around 1400 BCE. But the Greeks took them further. A Greek inventor named Ctesibius, working in Alexandria around 270 BCE, built what might be the most sophisticated water clock of the ancient world. He figured out one of the fundamental problems with water clocks, which is that the flow rate isn't actually constant. When the container is full, the water pressure at the hole is higher, so water flows out faster. As the level drops, the pressure drops, and the flow slows down. Your clock literally runs slower as the day goes on. Ctesibius solved this by adding a regulating mechanism, an intermediate reservoir that was kept at a constant level by a continuous inflow. The overflow drained away, and the regulated reservoir fed water at a steady rate into the measuring container. It's a feedback system, really. An early example of engineering a solution to maintain a constant output despite variable input. And his clocks were reportedly accurate to within about 15 minutes over the course of a day, which doesn't sound great by modern standards, but for 270 BCE, it was remarkable. The Chinese developed their own water clock traditions independently, and by the medieval period, Chinese engineers had built enormous water-powered astronomical clock towers. The most famous was built by Su Song in 1088 CE, a tower over 30 feet tall with a water-driven mechanism that turned an armillary sphere and a celestial globe, and it had little wooden figures that popped out at certain hours to announce the time. It's one of the great engineering achievements of the medieval world, and almost nobody in the West knows about it. But water clocks, for all their ingenuity, had limits. Water freezes. Water evaporates. The flow rate changes with temperature because viscosity changes. They're delicate, they're fiddly, and they're hard to make truly portable. Candle clocks were another option. You mark a candle at intervals and burn it, measuring time by how far it's burned down. King Alfred the Great of England supposedly used candle clocks in the 9th century to regulate his daily schedule. Incense clocks served a similar purpose in East Asia, where carefully calibrated sticks or coils of incense would burn at known rates. Some were even designed to drop small weights onto a metal plate at specific intervals, essentially creating an alarm clock out of incense and gravity. All of these, sundials, water clocks, candle clocks, incense clocks, share a common trait. They're all trying to do the same fundamental thing. Take some physical process that happens at a roughly steady rate and use it to measure the passage of time. Shadow movement, water flow, burning. That's really what every clock in history does, from the most ancient to the most modern. Find something that repeats or progresses steadily, and count the repetitions or measure the progress. The entire history of timekeeping is the search for a more and more stable, more and more consistent physical process to count. And that brings us to one of the most important inventions in the history of civilization. Something so ubiquitous that you probably don't even think of it as a technology, the mechanical clock, and specifically, the thing that made mechanical clocks possible, a mechanism called the escapement. Now, the basic idea of a mechanical clock is this. You have a source of energy, usually a weight hanging from a cord wrapped around a drum, so gravity is pulling the weight down and turning the drum. That turning motion drives a series of gears, and the gears move the hands of the clock. Simple enough in concept. But here's the problem. If you just let gravity pull the weight down, it'll fall as fast as it can, the gears will spin freely, and the whole thing will be over in seconds. You need something to slow it down, to regulate the release of energy into controlled, even measurable ticks. That something is the escapement. The escapement is a mechanism that alternately blocks and releases the gear train, letting it advance by exactly one tooth at a time, at a controlled rate. Think of it like a turnstile. The energy wants to push through, but the turnstile only lets one person through at a time. Click, click, click. The earliest form we know about is called the verge escapement, and it appeared in Europe sometime in the late 13th century. Nobody knows exactly who invented it. There's no single eureka moment we can point to, no lone genius in a workshop. It seems to have emerged gradually, probably in monastic settings, because monks had a powerful motivation to track time accurately. Their entire daily schedule was built around the canonical hours, the cycle of prayers that structured monastic life. They needed to know when to pray, and they needed to know it reliably, even on cloudy days, even in the middle of the night. The earliest mechanical tower clocks started appearing in European cities in the 1280s and 1290s. There are records of a clock at Dunstable Priory in England in 1283, and one at the cathedral in Exeter around the same time. These early clocks didn't even have faces or hands. They just rang bells. The word clock itself comes from the medieval Latin clocca, meaning bell. A clock was, originally, just a bell that rang at the right time, And these early clocks were not very accurate. They could drift by as much as 15 minutes or even half an hour per day, which meant someone had to reset them regularly using a sundial. Which is a funny thought, this big, expensive mechanical marvel in the church tower. And you still need the sundial out in the courtyard to keep it honest. But even with their limitations, mechanical clocks changed everything. They changed the way people thought about time itself. Before mechanical clocks, time was natural. It was the sun, the seasons, the rhythm of agriculture. After mechanical clocks, time became something measured by a machine, something that ticked along at a constant rate, regardless of whether the sun was shining or not. And this is when equal hours, what we'd now call equinoctial hours, each one exactly 1/24th of a full day, started to replace the old seasonal hours. Because mechanical clocks couldn't easily produce hours that changed length with the seasons. They ticked at a constant rate, so they naturally produced hours of constant length. The technology didn't adapt to the old system. The old system adapted to the technology. By the 14th century, equal hours were becoming the norm across Europe, and the ancient tradition of seasonal hours that had lasted for over 2,000 years quietly faded away. And this is one of those moments in history that's easy to gloss over, but it's worth sitting with for a second. The way we experience time, fixed hours, same length in summer and winter, abstract and mechanical and detached from the sun, that's not natural. That's an artifact of a specific technology invented in medieval Europe. We live inside a framework that monks and blacksmiths cobbled together 700 years ago, and we've so thoroughly internalized it that it feels like time itself. But it's not time itself. It's a clock. And clocks, as we're about to see, kept getting more precise, more demanding, more intertwined with every aspect of human life, in ways that those medieval monks could never have imagined. And the first place you really see that is in the cities. Because by the 1400s, town clocks weren't just curiosities anymore. They were civic infrastructure. They regulated market hours. They told workers when to start and stop. They coordinated the opening and closing of city gates. And if you were a merchant or a craftsman in, say, 15th century Nuremberg or Florence, the clock in the town square wasn't just telling you what time it was telling you what to do. Time had become a form of social control, and honestly, it still is. Think about your own day, your alarm, your commute, your meetings, your deadlines. That entire structure traces back to these medieval tower clocks ticking away in market squares, training people to organize their lives not around sunlight, but around the hour. But here's the thing about those early mechanical clocks. They were terrible. I mean, by modern standards, just spectacularly bad at keeping time. A good tower clock in the 1400s might drift by 15 minutes a day. Some were worse. They needed constant adjustment, constant maintenance, and someone had to wind them, usually by hauling heavy stone weights back up on their ropes, sometimes multiple times a day. The verge escapement that made them possible was clever, but it had a fundamental problem. Its timekeeping depended on how much force the driving weight was exerting, which changed as the weight descended and the gears wore. The rate wasn't truly constant. It wandered. And for a couple of centuries, that was fine. 15 minutes a day? Nobody really cared. Most people didn't even have a way to measure intervals shorter than an hour. Clocks had hour hands, just hour hands, no minute hand, because what would be the point? The clock wasn't accurate enough to make a minute hand meaningful. But as commerce grew, as navigation became more critical, as science started asking more precise questions about the natural world, that sloppiness became a real problem. And the solution, when it finally came, was one of those beautiful moments where someone looks at something people had known about for centuries and sees it with completely new eyes. Galileo Galilei, Florence, around 1583. He's a young man, maybe 19 or 20, sitting in the Cathedral of Pisa. At least, that's how the story is traditionally told, and some historians question the details, but the core of it holds up. He's watching a chandelier swing back and forth, maybe set in motion by a draft or by someone who'd pulled it aside to light it, and he notices something. Whether the chandelier swings in a wide arc or a narrow one, each swing seems to take the same amount of time. He checks this against his own pulse, which, isn't the most precise instrument, but it's what he has. And he finds that the period of a pendulum swing is roughly constant regardless of the amplitude. This property is called isochronism, and it's one of those observations that seems simple but cracks open an entire field. Now, Galileo didn't actually build a pendulum clock. He sketched designs for one late in his life, around 1637, when he was old and blind, and his son Vincenzo tried to construct one after Galileo's death in 1642, but never finished it. The person who actually made the pendulum clock a reality was Christian Huygens, a Dutch mathematician and physicist, and he did it in 1656. And this is where the story of timekeeping takes a genuine leap forward, not an incremental improvement, but a revolution in precision. Huygens was brilliant, one of those polymaths that the 17th century seemed to produce so reliably. He worked on optics, he discovered Titan, Saturn's largest moon, he developed a wave theory of light. But his pendulum clock might be his most practically impactful contribution. What he realized was that if you replaced the verge escapement's foliote, that weighted bar swinging back and forth, with a pendulum, you'd get a regulator whose period depended almost entirely on its length and the force of gravity, not on the driving force of the mechanism. A pendulum of a given length swings at a given rate, period. You don't need to worry about how much weight is on the driving cord or how worn the gears are. The pendulum just does its thing. And the improvement was staggering. Where a good verge and foliate clock might lose 15 minutes a day, Huygens's first pendulum clock was accurate to about 15 seconds a day. That's a 60-fold improvement, almost overnight. Suddenly, minute hands made sense, and within a few decades, as the design was refined, pendulum clocks were accurate to about 10 seconds a day, then 5, then even better. By the early 1700s, the best pendulum clocks in observatories were keeping time to within a second or two per day. For the first time in human history, you could meaningfully talk about minutes and seconds as real, measurable units of daily life. Let's talk about that for a second, because it's easy to hear 15 seconds a day and think, okay, that's nice, but what does it actually change? What it changes is everything that depends on precise coordination, and the most urgent, most dramatic, most consequential of those things in the 17th and 18th centuries was navigation at sea. Here's the problem. If you're a sailor in the middle of the Atlantic Ocean, you need to know two things: your latitude and your longitude. Latitude is relatively easy. You can figure it out by measuring the angle of the sun at noon or the angle of Polaris at night. Sailors had been doing that for centuries. But longitude? Longitude is a nightmare. There's no star that tells you how far east or west you are. The only reliable way to determine your longitude is to know the exact time at some reference location, say London, and compare it to local time wherever you are. The Earth rotates 360 degrees in 24 hours, which works out to 15 degrees per hour. So if your clock says it's noon in London, but the sun is directly overhead where you are, you know you're at 0 degrees longitude. You're right on the prime meridian. If your clock says it's noon in London, but local noon was 2 hours ago, you're 30 degrees east. Makes sense, right? But here's the kicker. For this to work, you need a clock that keeps London time accurately across weeks or months at sea, on a rolling, pitching, salt-sprayed ship, through temperature swings from the North Atlantic to the tropics. And pendulum clocks, for all their brilliance, are useless on a ship. A pendulum needs to hang straight down under the influence of gravity. Put it on a swaying deck, and it goes haywire. Huygens actually tried to build marine pendulum clocks. He experimented with suspending them on gimbals, even tried 2 pendulums swinging in opposition to cancel out the ship's motion. None of it worked well enough. And this wasn't an academic problem. People were dying. Ships were wrecking on coastlines they didn't know were there because they couldn't determine their longitude. In 1707, a British naval fleet under Admiral Sir Cloudesley Shovel miscalculated their position in the Atlantic and ran aground on the Isles of Scilly, off the southwestern tip of England. 4 ships sank. Between 1,400 and 2,000 sailors drowned. It was one of the worst maritime disasters in British naval history, and it was fundamentally a timekeeping problem. 7 years later, in 1714, the British Parliament passed the Longitude Act, offering a prize of up to £20,000, an enormous fortune, equivalent to several $1,000,000 today, to anyone who could devise a practical method for determining longitude at sea to within half a degree. That translates to keeping time accurate to within about 2 minutes over the course of a voyage lasting weeks. The scientific establishment, led by figures like the astronomer Royal Neville Maskelyne, favored astronomical solutions. The so-called lunar distance method, which involved measuring the angle between the moon and certain stars, and then doing a pile of complex calculations. It worked, in theory, but it was brutally difficult in practice, requiring skilled navigators and clear skies and tables that took years to compile. And then there was John Harrison. And his story is one of the great underdog narratives in the history of engineering. Harrison was a carpenter from Barrow-upon-Humber in Lincolnshire. He was self-taught. He had no formal education in clockmaking or science. He was, by the standards of the London scientific elite, a nobody. But he was obsessively, almost unreasonably talented at understanding how mechanical things moved and how to make them move more precisely. He'd already built remarkably accurate long-case clocks using wooden gears. He'd figured out that lignum vitae, an incredibly dense tropical hardwood, was naturally oily enough that wooden gears made from it didn't need lubrication, which meant they didn't gum up or attract dust. That's the kind of mind he had. He didn't just solve problems. He solved the problems behind the problems. Harrison spent the better part of his adult life, decades, working on the longitude problem. His first marine timekeeper, now called H1, was completed around 1735. It was a big, complex, beautiful machine, about 4 feet on a side, with interconnected balance bars and spring mechanisms designed to compensate for the motion of a ship. It performed well on a trial voyage to Lisbon, but Harrison wasn't satisfied. He built H2, then H3, each one taking years. H3 alone took him 19 years. And then, in a move that surprised everyone, he changed direction entirely. Instead of building another large, complex machine, he built something small, a watch. H4, completed in 1759, was about 5 inches in diameter, basically a large pocket watch, and it was a masterpiece. H4 was tested on a voyage to Jamaica in 1761. When the ship arrived after 81 days at sea, The watch had lost only 5 seconds. 5 seconds over 81 days. That's accuracy that blows away the Longitude Act's requirements. It should have been an immediate triumph. But this is where the human drama gets painful, because the Board of Longitude, heavily influenced by Maskelyne and others who favored the astronomical method, kept moving the goalposts. They demanded more trials. They demanded that Harrison explain every detail of his construction so that others could replicate it. They awarded him partial payments, but withheld the full prize for years. Harrison was in his 70s, then his 80s, fighting for recognition he'd clearly earned. It wasn't until 1773, when Harrison was 80 years old, that King George III personally intervened and Parliament finally awarded him the bulk of the prize money. He died 3 years later. And here's what's worth sitting with about Harrison's story. This was a carpenter who solved one of the greatest scientific and engineering challenges of his century, and he did it not through theory, but through craft, through an almost inhuman sensitivity to the behavior of metals and springs, and friction and temperature. He invented mechanisms to compensate for temperature changes affecting the spring rate. He devised new types of escapements. He figured out how to reduce friction to almost nothing in an era before modern lubricants. Every one of those innovations was a tiny engineering marvel, and together they produced something that changed the world. Because once you can determine longitude reliably, you can navigate the oceans safely. Trade routes become predictable, naval power becomes projectable, maps become accurate. The British Empire, in a very real sense, was built on the back of accurate timekeeping. But Harrison's watches, brilliant as they were handcrafted one-offs, impossibly expensive, impossibly labor-intensive. The real transformation came when other clockmakers figured out how to produce reliable marine chronometers in quantity. By the early 1800s, firms like Thomas Earnshaw and John Arnold in London were manufacturing chronometers that were affordable enough, well, affordable for a ship's captain, at least, to become standard equipment on naval and merchant vessels. And every single one of them carried, embedded in its mechanism, ideas that Harrison had pioneered. Meanwhile, back on land, something else was happening with clocks that would reshape daily life in a completely different way. Because as clocks got more accurate and more widespread, a new problem emerged, one that nobody had really thought about before. And that problem was this: whose time is the right time? If you're in London and your clock says noon, and someone in Bristol, 120 miles to the west, has a clock that also says noon, those two noons don't actually happen at the same moment. Bristol is far enough west that the sun reaches its zenith about 10 minutes later than in London. So Bristol's local noon is 10 minutes after London's local noon. And for most of history, that was perfectly fine. Every town kept its own local time, set by its own sundial or its own church clock, and nobody worried about the discrepancy because it didn't matter. If it took you 2 days to travel from London to Bristol by horse, who cared about 10 minutes? But then came the railways, and the railways, as they had a habit of doing, changed absolutely everything about how people thought about distance and time. Because suddenly, for the first time in human history, you could move fast enough that those 10 minutes actually mattered. Think about what rail travel did. Before the 1830s, the fastest most people ever moved was the speed of a galloping horse, maybe 15 miles an hour on a good road. At that pace, you'd barely notice the drift in local time from one town to the next. but a train could cover that same distance in a fraction of the time. The Great Western Railway, which connected London to Bristol starting in 1841, could get you there in a few hours. And suddenly, you had a real, practical, dangerous problem. Because the timetable said your train departed Bristol at, say, 11 o'clock. But 11 o'clock according to whom? Bristol time? London time? The time on the station clock? The time on the conductor's pocket watch? And what if those were all slightly different? This wasn't a philosophical question. This was a question that could get people killed. Early railways were single track for long stretches, which meant trains going in opposite directions had to be carefully scheduled to use passing loops. Little sidings where one train would pull over and wait for the other to go by. If the station master at one end was working on local time and the station master at the other end was working on a time that was 7 or 8 minutes different, well, you can imagine what could happen. And it did happen. There were collisions. There were near misses that were even more numerous. The whole system was a mess. So the railways did something radical. They just picked a time, one time, and said, "This is the time we're using, everywhere, on every line, at every station." And the time they picked was London time, Greenwich time, specifically the time kept by the Royal Observatory at Greenwich, which had been the reference point for naval chronometers for decades. Starting in the 1840s, the Great Western Railway and then other railway companies began distributing Greenwich time along their telegraph lines to station clocks across the country. They called it railway time. And if you were in Exeter, where local noon was about 14 minutes later than Greenwich noon, too bad. The station clock said what Greenwich said, and your train left when the station clock said it left. Here's what's fascinating about this. It wasn't the government that standardized time in Britain. It wasn't Parliament. It wasn't the Royal Observatory issuing some decree. It was a private business decision made by railway companies because they needed their operations to not be chaotic. The technology drove the policy. The trains needed a single time standard to function safely, so the trains created one. And then everybody else just sort of went along with it. Towns started setting their public clocks to railway time because it was more convenient. If you wanted to catch your train, you needed to be on railway time, and if your town clock was on railway time, then your whole life gradually shifted to railway time. Some towns resisted for a while. There's a wonderful detail about the clock on the Tom Tower at Christ Church in Oxford, which for years showed 2-minute hands, one for local Oxford time and one for Greenwich time, about 5 minutes apart. But eventually, even Oxford gave in. It wasn't until 1880 that Parliament actually passed the Statutes, Definition of Time Act, which legally established Greenwich Mean Time as the official time for all of Great Britain. But by then, the railways had already done the work. The law was just catching up to reality. And this is a pattern you see over and over in the history of timekeeping. The practical need comes first, the technology adapts, and then the legal and social structures follow, sometimes decades later. Now, Britain was one country, and a relatively small one at that. The time difference between the eastern and western edges was only about half an hour. But think about what happens when you try to do this across a continent. Think about the United States in the 1870s. The country stretches across roughly 60 degrees of longitude. That's 4 hours of solar time difference between the East Coast and the West Coast. And in that era, there was no national time standard at all. Every city kept its own local time. When it was noon in Washington, D.C., It was about 12 minutes before noon in New York, and about 24 minutes past noon in Boston. Wait, no, that's not right. Let me think about this. New York is slightly west of Boston, so New York's local noon comes a few minutes after Boston's, and Washington is slightly south and west of New York. The point is, every city was different, and not by trivial amounts. By one count, there were over 300 distinct local times in use across the United States in the 1870s. 300. And every single railroad had to deal with this chaos. The person who did the most to fix this, and this is one of those names that deserves to be far more famous than it is, was a Canadian railway engineer named Sanford Fleming. Fleming had a personal experience that crystallized the problem for him. In 1876, he was traveling in Ireland and missed a train because a printed timetable listed a departure as PM when it should have been AM, or possibly the other way around. The exact details vary depending on who's telling the story. But the experience stuck with him. He started thinking seriously about time standardization, and by 1879, he was proposing a system of worldwide standard time zones, 24 zones, each 15 degrees of longitude wide, each exactly 1 hour apart, all referenced to a single prime meridian. Now, Fleming wasn't the only person thinking about this. American railroad companies had been struggling with the problem for years, and a group of railroad superintendents had been working on their own solution. The key figure on the American side was William F. Allen, the secretary of the General Time Convention, which was basically a coordinating body for the railroads. Allen took the general concept of time zones, which Fleming and others had been promoting, and turned it into a specific practical plan that the railroads could actually implement. He divided the continental United States into 4 time zones: Eastern, Central, Mountain, and Pacific, with boundaries that followed railroad routes rather than neat lines of longitude, because the railroads cared about operational convenience, not geometric elegance. And on November 18, 1883, a date sometimes called the Day of Two Noons, the railroads just did it. They switched. At noon Eastern Time, every railroad clock in the Eastern Zone was set to the new standard time. Cities that had been slightly ahead found their clocks jumping backward. Cities that had been slightly behind found them jumping forward. In some places, noon literally happened twice, the local noon, and then a few minutes later, the new standard noon. Hence the name. And again, just like in Britain, this wasn't a government action. Congress didn't pass a law establishing time zones in 1883. The railroads just decided, and the rest of the country followed. It wasn't until 1918, 35 years later, that Congress passed the Standard Time Act, which legally established the time zones that the railroads had been using for a generation. By then, of course, it was a formality. But here's where it gets really interesting, because the question of time zones leads inevitably to a much bigger question. If you're going to have time zones, you need a prime meridian. You need a line of 0 longitude, a reference point that everything else is measured from. And in 1884, delegates from 25 nations gathered in Washington, D.C., for the International Meridian Conference to settle this once and for all. The politics of this were delicious. The French wanted the prime meridian to run through Paris. The British, of course, wanted it at Greenwich. The Americans, who were hosting the conference, were happy to support Greenwich because American sailors were already using British naval charts, which were already based on Greenwich. There were proposals for a neutral meridian, running through the Azores, or through the Bering Strait, or through some other location that wouldn't give any one nation the symbolic prestige of being the center of the world's time system. In the end, pragmatism won. Greenwich was already the de facto standard. Something like 72% of the world's shipping was already using charts based on the Greenwich meridian. So by a vote of 22 to 1, with San Domingo voting against and France and Brazil abstaining, the Greenwich meridian became the world's prime meridian. The French, characteristically, continued to use Paris time internally for another 27 years, finally adopting Greenwich-based time in 1911. And even then, they couldn't quite bring themselves to call it Greenwich Mean Time. They called it Paris Mean Time, retarded by 9 minutes and 21 seconds, which is one of the most perfectly French things I've ever heard. So by the end of the 19th century, the world had something it had never had before: a shared framework for time, time zones, a prime meridian, a common reference. And this might seem like just an administrative convenience, like agreeing on which side of the road to drive on. But it was deeper than that. It represented a fundamental shift in what time meant. For all of human history up to that point, time had been local. Your time was your time, defined by your sun, your noon, your place on the earth. The idea that someone in an office in Greenwich could tell you what time it was in your town, that your lived experience of the sun's position was somehow less correct than a number transmitted over a telegraph wire, that was genuinely strange. It was a kind of abstraction, a separation of time from the physical world, and its attachment instead to a human system, a grid, a convention. And this abstraction was about to get even more dramatic, because just as the world was settling into its new system of standardized clock time, a young patent clerk in Bern, Switzerland, was thinking about what time actually meant at a much more fundamental level. His name, of course, was Albert Einstein. And in 1905, he would publish a paper that would take everything we thought we knew about time and turn it completely inside out. But to understand what Einstein did and why it mattered, you need to first understand the problem he was trying to solve. And that problem, strangely enough, also had to do with synchronizing clocks, not across a railway network, but across the entire universe. Because by the late 1800s, physicists had discovered something deeply troubling about the speed of light, something that seemed to contradict everything they thought they knew about how the universe worked. And to get at this, we need to talk about something that might seem unrelated at first. We need to talk about light itself. See, by the mid-1800s, physicists had figured out that light was a wave. James Clerk Maxwell, this brilliant Scottish physicist working in the 1860s, had shown that electricity and magnetism were really two aspects of the same thing, and that when you wiggled an electric charge back and forth, it sent out ripples, electromagnetic waves that traveled at a very specific speed, about 186,000 miles per second, or roughly 300,000 kilometers per second. And here's what was strange about that number. It was just a number. It popped out of Maxwell's equations like a constant of nature, with no reference to anything else. It didn't say 186,000 miles per second relative to the ground, or relative to the sun, or relative to whatever emitted the light. It just said, this is the speed, full stop. Now, that might not immediately sound like a problem, but think about it for a second. Think about how speed normally works. If you're standing on a train platform and a train goes past you at 60 miles per hour, you measure its speed as 60. But if you're on another train going 40 miles per hour in the same direction, that first train only seems to be going 20 miles per hour relative to you. Speeds add and subtract. That's just basic common sense, and it's also basic Newtonian physics. Galileo had described this principle centuries earlier. The idea that there's no absolute motion, only relative motion. You can't tell if you're truly moving or still without looking at something else. But Maxwell's Equations seemed to be saying that light didn't play by these rules. Light had one speed, and that was that. So physicists had a question. One speed relative to what? And the answer they came up with was something called the ether. The luminiferous ether. This hypothetical substance that was supposed to fill all of space, providing a medium for light waves to travel through, the way water provides a medium for ocean waves, or air provides a medium for sound. The idea was that light traveled at 186,000 miles per second relative to the ether, and since the Earth was moving through the ether as it orbited the Sun, you should be able to detect that motion. You should be able to measure a difference in the speed of light, depending on whether you aimed your measurement in the direction of Earth's motion or perpendicular to it. It's like swimming in a river. You go faster with the current and slower against it. So in 1887, two American physicists, Albert Michelson and Edward Morley, set up an incredibly precise experiment to detect exactly this. They built a device called an interferometer in a basement in Cleveland, Ohio, mounted on a massive sandstone slab floating on mercury to eliminate vibrations. The idea was elegant. Split a beam of light in two, send the halves in perpendicular directions, bounce them off mirrors, and bring them back together. If the Earth was moving through the ether, one beam would have traveled slightly faster than the other, and when they recombined, they'd be slightly out of sync. You'd see an interference pattern, a telltale shift in the light. They found nothing. No shift, no difference. No matter which direction they aimed the apparatus, no matter what time of year they measured, and remember, the Earth is moving at about 67,000 miles per hour around the Sun, so the ether wind should have been substantial. The speed of light came back the same every single time. This was, to put it mildly, a crisis. The Michelson-Morley result was one of the most famous failed experiments in the history of science, and it's a beautiful example of how a null result can be more important than a positive one. Physicists tried to explain it away. Hendrik Lorentz and George Fitzgerald independently proposed that objects moving through the ether physically contracted in the direction of motion, that the arm of the interferometer pointing in the direction of Earth's motion was literally getting shorter, by just enough to compensate for the expected time difference, which is a wild idea when you think about it. They were saying that motion through the ether physically squished matter, and the math actually worked. Lorentz developed a whole set of transformation equations that could account for the null result, but it felt like a patch, a fix bolted onto the theory to save it. There was no explanation for why objects would contract this way. It was just convenient. And this is where Einstein comes in. And here's the thing about Einstein in 1905. He wasn't a professor. He wasn't at a prestigious university. He was a 26-year-old technical expert, third class, at the Swiss Federal Patent Office in Bern. He'd struggled to find an academic position after finishing his degree. He spent his days evaluating patent applications, many of which involved electrical devices, and, interestingly, systems for synchronizing clocks. Clock synchronization. Think about that. Here was a man whose day job involved thinking about how to coordinate time signals between different locations, and in his spare time, he was pondering the deepest questions about what time and simultaneity actually meant. Einstein's approach was radically different from Lorentz's. Instead of trying to save the ether and explain why experiments couldn't detect it, Einstein simply threw it away. He started from two postulates, two assumptions, and followed them to their logical conclusions, no matter how strange those conclusions turned out to be. The first postulate was the principle of relativity. The laws of physics are the same for everyone moving at a constant speed. No experiment you can do inside a sealed, smoothly moving room will tell you whether you're moving or stationary. This wasn't new. Galileo had said essentially the same thing. Einstein's second postulate was the revolutionary one. The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. Not relative to the ether, not relative to anything in particular, just the same for everyone, always, period. Now, those two postulates seem almost innocuous when you first hear them. But here's what's wild. They're contradictory if you hold on to the old Newtonian ideas about time and space. Think about it. If I'm standing still and I shine a flashlight, I measure the light going at 186,000 miles per second. Fine. But now suppose you're flying past me at half the speed of light. In Newton's world, you should measure that same light beam going at only half the speed. 186,000 minus 93,000, or 93,000 miles per second. But Einstein's second postulate says no. You also measure it at 186,000 miles per second, the full speed. Same as me. How can that possibly be true? The answer, and this is the heart of special relativity, is that time itself is not what we thought it was. For both of us to measure the same speed of light, something else has to give. And what gives is time. Time passes at different rates for observers moving at different speeds relative to each other. This is called time dilation. And it's not a metaphor. It's not a philosophical position. It's not an optical illusion. It is a physical fact about the universe. Let me try to make this concrete. Einstein loved thought experiments, so let's use one. Imagine you're on a train. Einstein was fond of trains. And you have a simple clock. This clock works by bouncing a pulse of light between two mirrors, one on the floor and one on the ceiling. Every time the light makes a round trip, tick, that's 1 unit of time. Simple. Now, from your perspective on the train, the light goes straight up and straight down. The distance is just the height between the mirrors, and the time for each tick is that distance divided by the speed of light. But now imagine I'm standing on the platform, watching your train go past. From my perspective, the light isn't going straight up and down. It's going diagonally, because while the light travels from the floor mirror to the ceiling mirror, the train has moved forward. The light has to cover a longer diagonal path. But, and this is the key, the speed of light is the same for me as it is for you. Same speed, longer path. That means each tick of your clock takes longer as measured by me. Your clock, from my perspective, is running slow. And it's not just that particular light clock. It's every clock. It's every physical process. Your heartbeat, the vibration of atoms, the decay of radioactive particles, your thoughts, everything runs slower for a moving observer as seen by a stationary one. Time itself dilates. Here's what's really going to bend your mind, though. From your perspective on the train, you're the one who's stationary, and I'm the one moving backward on the platform. So from your point of view, my clocks are the ones running slow. And you're not wrong. Neither of us is wrong. There's no absolute answer to whose clock is really running at the right speed, because there's no absolute time. There's no universal clock ticking away somewhere that keeps the real time. Every reference frame has its own equally valid time. Think about what that means in the context of everything we've talked about so far. All that effort. The Egyptians with their shadow clocks, The medieval monks with their verge escapements, Huygens with his pendulum, Harrison with his marine chronometers, the railway companies stringing telegraph wires to synchronize station clocks, the diplomats at the 1884 conference arguing over where to put the prime meridian. All of that was built on an assumption so deep that nobody even thought to question it. The assumption that time was universal, that a second was a second was a second, everywhere, for everyone, always. That if you had a perfect clock, it would tick at the same rate whether it was in London or on the moon or on a spaceship hurtling through the cosmos. Einstein showed that this assumption was wrong. Now, at everyday speeds, the speeds of trains and planes and even rockets, the effect is incredibly tiny. At the speed of a commercial airplane, time dilation amounts to a few nanoseconds per hour, billionths of a second. You're not going to notice that your watch runs slow after a cross-country flight, but the effect is real, and it's been measured. In 1971, physicists Joseph Haffel and Richard Keating put cesium atomic clocks on commercial airliners, flew them around the world, eastward and westward, and compared them to reference clocks on the ground. The clocks disagreed by exactly the amount that relativity predicted. Nanoseconds, yes, but exactly the right number of nanoseconds. And here's where this stops being abstract physics and starts being something that affects your daily life in ways you probably don't realize. Because there's a system you almost certainly use every single day that would fail completely without accounting for relativistic time dilation. It's the Global Positioning System, GPS. The satellites in the GPS constellation orbit the Earth at about 14,000 kilometers per hour. That's fast enough for special relativistic time dilation to make their onboard clocks tick about 7 microseconds per day slower than clocks on the ground. 7 millionths of a second per day. Sounds trivial, right? But GPS works by measuring the travel time of radio signals to within nanoseconds. A 7 microsecond error would translate to a position error of about 2 kilometers per day. Your phone's map would be useless within a single morning. But actually, it's even more complicated than that, because Einstein wasn't done. Special relativity was published in 1905, but it only dealt with observers moving at constant speeds. It took Einstein another 10 years. 10 years of what he later called the hardest intellectual struggle of his life, to extend the theory to include acceleration and gravity. And when he did in 1915, with general relativity, time got even stranger, because it turns out that gravity also affects the flow of time. Clocks in stronger gravitational fields tick slower than clocks in weaker gravitational fields. A clock on the ground floor of a building runs ever so slightly slower than a clock on the top floor, because it's closer to the center of the Earth, deeper in the gravitational well. And for those GPS satellites orbiting high above the Earth where gravity is weaker, this general relativistic effect makes their clocks tick faster by about 45 microseconds per day. So you've got two competing effects. Special relativity slowing the satellite clocks down by 7 microseconds, and general relativity speeding them up by 45 microseconds, for a net gain of about 38 microseconds per day. The GPS system has to correct for this constantly, adjusting the frequency of the satellite clocks before they're even launched, pre-tuning them to tick at a slightly different rate so that once they're in orbit, they'll match ground clocks. Without Einstein's theories, both of them, the system simply wouldn't work. So here we are, We started the evening with shadows on the ground and candles burning in monastery cells. And now we're talking about the fabric of space-time bending around the Earth and warping the flow of time itself. And what I find so beautiful about this story is the thread that runs through all of it. This persistent human need to measure time more precisely, and how every leap in precision reveals something new about what time actually is. The Egyptians needed to divide the day for practical purposes and discovered that hours could be unequal. Huygens needed a better clock and discovered the isochronism of pendulums. Harrison needed to find longitude and pushed mechanical timekeeping to its absolute limits. And Einstein, thinking about what it means to synchronize two clocks that are far apart, discovered that time itself is relative. But Einstein's revolution, as profound as it was, still left one enormous question unanswered. Maybe the biggest question of all. Because relativity tells you that time passes at different rates depending on your speed and your gravitational environment, and it tells you how to calculate those differences with extraordinary precision. But it doesn't tell you why time moves forward at all. Think about that. Every equation in physics, Newton's laws, Maxwell's equations, even Einstein's own field equations of general relativity, works perfectly well if you run time backward. If you filmed a billiard ball bouncing off a cushion and played the film in reverse, the reversed motion would obey Newton's laws just as well as the forward motion. The equations don't care which direction time goes, and yet we experience time as having a very definite direction. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. We remember the past, but not the future. There's an arrow to time, and it points in only one direction, and the reason for that arrow takes us into one of the most fascinating corners of physics, the science of heat, energy, and disorder, the science of thermodynamics. And the story starts, like so many good stories in science, with a very practical problem. Not a philosophical question about the nature of time, but an engineering question about how to get more useful work out of a steam engine. It's the late 1700s, the early 1800s. The Industrial Revolution is transforming Britain and spreading across Europe. Steam engines are pumping water out of mines, driving factory machinery, and beginning to pull trains along iron rails. And the big question on everyone's mind isn't, what is time? It's, how do we make these engines more efficient? Because fuel costs money. Coal costs money. And if you can get more work out of each ton of coal, you make more profit. Simple as that. Enter a young French military engineer named Sadi Carnot. Born in 1796, son of a famous revolutionary general and politician, Lazare Carnot. Sadi was brilliant, quiet, and deeply patriotic. He looked at Britain's industrial dominance, all those steam engines powering an empire, and he wanted to understand the fundamental principles behind them. Not just how to build a better engine through tinkering and trial and error, but the theoretical limits. What's the most work you could possibly extract from a given amount of heat? Is there a ceiling? And if so, what determines it? In 1824, when he was just 28 years old, Carnot published a slim book called Reflections on the Motive Power of Fire. And in it, he laid out something remarkable. He showed that the efficiency of any heat engine, any engine that converts heat into work, depends only on the temperature difference between its hot source and its cold sink. The bigger the temperature difference, the more work you can extract. But here's the crucial part. You can never convert all the heat into work. Some heat always has to flow to the cold side. Always. There's no way around it. Carnot died just 8 years later, in 1832 during a cholera epidemic in Paris. He was 36. Most of his papers were burned, as was common with cholera victims' belongings, and his little book was largely ignored for over a decade. But the idea was there, waiting. It took other minds to pick it up and run with it. Rudolf Clausius in Germany, and William Thomson, later Lord Kelvin, in Scotland, working through the 1840s and 1850s, formalized what Carnot had intuited into the laws of thermodynamics. And the one that matters most for our story about time is the second law. Now, the second law of thermodynamics has been stated in many different ways over the years, and they all turn out to be equivalent, which is kind of amazing. Clausius put it this way: heat flows spontaneously from hot to cold, never the other way around. Kelvin put it slightly differently. You cannot build a perfect engine that converts heat entirely into work with no waste. But the deepest, most general way to state it came from Clausius himself in 1865, when he introduced a new concept, a quantity he called entropy. Entropy. It's one of those words that gets thrown around a lot, often loosely, and it's worth taking a moment to really sit with what it means. Here's one way to think about it. Imagine you have a box divided in half by a partition. On one side, you've got a gas, say, air molecules bouncing around. On the other side, nothing, a vacuum. Now you remove the partition. What happens? The gas rushes to fill the whole box. Every molecule is still bouncing around according to Newton's laws, and each individual collision is perfectly reversible. If you could somehow reverse every molecule's velocity at the same instant, they'd all retrace their paths and end up back on one side. The laws of physics allow it. But it never happens. You will never see a gas spontaneously gather itself into one half of a box. Never. Not because it's impossible for any individual molecule, but because it's astronomically unlikely for all of them to do it at once. And that's entropy at its heart. It's about probability. It's about the number of ways the microscopic pieces of a system can be arranged. When the gas is all on one side, there's a relatively small number of arrangements. Every molecule has to be in that one half. When the gas fills the whole box, there's an enormously larger number of possible arrangements, and systems naturally evolve from less probable states to more probable states, simply because there are so many more ways to be in the probable state. That's it. That's the second law. Entropy tends to increase because there are overwhelmingly more disordered arrangements than ordered ones. And the person who made this connection, who showed that the second law of thermodynamics isn't some mysterious decree, but a consequence of statistics and probability, was an Austrian physicist named Ludwig Boltzmann. And his story is one of the most poignant in all of science. Boltzmann was born in Vienna in 1844. He was a large, energetic, passionate man, bushy beard, thick glasses, a booming laugh. He loved music, he loved nature, and he loved physics with an intensity that bordered on obsession. In the 1870s and 1880s, he developed what we now call statistical mechanics, the idea that the behavior of gases, heat, and thermodynamic properties in general could be explained by the statistical behavior of enormous numbers of atoms and molecules. This seems obvious now, but at the time it was deeply controversial. And the controversy wasn't just about the math, it was about whether atoms even existed. In the late 19th century, a significant faction of physicists and philosophers, led by figures like Ernst Mach and Wilhelm Ostwald, argued that atoms were just a convenient fiction, a mathematical trick. They believed that energy, not matter, was the fundamental reality, and that science should deal only with directly observable quantities. Boltzmann's entire framework depended on atoms being real, and his opponents attacked him relentlessly. Think about what that must have felt like. You've spent your career building this beautiful theoretical structure, and some of the most respected scientists in your field are telling you it's built on sand, that atoms don't exist, that your life's work is meaningless philosophy, not real physics. Boltzmann fought back, passionately and sometimes bitterly. He gave lectures, wrote papers, engaged in public debates, but the attacks took their toll. He suffered from severe depression throughout his life, what we would probably now diagnose as bipolar disorder. And in 1906, while on vacation with his family near Trieste, Ludwig Boltzmann hanged himself. He was 62 years old. Here's the thing that makes this story so heartbreaking. Just a few years later, literally within a decade of his death, the tide turned completely. Einstein's 1905 paper on Brownian motion provided strong evidence that atoms were real. Jean Perrin's experiments confirmed it. By 1910 or so, virtually no serious physicist doubted the existence of atoms anymore. Boltzmann was vindicated, but he never lived to see it. On his tombstone in Vienna, they engraved his most famous equation, S equals K log W. Entropy equals Boltzmann's constant times the logarithm of W, where W is the number of microstates, the number of different ways the microscopic components of a system can be arranged while still looking the same from the outside. It's carved right there in the stone. And that equation is, in a very real sense, the equation that explains the arrow of time. Because here's what Boltzmann showed us. The reason time has a direction, the reason eggs break and don't unbreak, the reason your coffee cools down, the reason you age, is that the universe started in an extraordinarily low entropy state, a state of remarkable order. And it's been evolving toward higher entropy ever since, simply because there are so many more ways to be disordered than ordered. The arrow of time is the arrow of increasing entropy. Let that sink in for a moment. The direction of time, this thing we experience so viscerally, so fundamentally, every single moment of our lives, isn't written into the basic laws of physics. Those laws are time-symmetric. The arrow of time emerges from statistics, from probability, from the simple fact that if you start in an unlikely arrangement, you'll almost certainly move toward a more likely one. And this connects back to everything we've been talking about. All those clocks, the sundials, the water clocks, the pendulums, the marine chronometers, the atomic clocks, they all work because of irreversible processes happening somewhere in the system. The shadow moves because the Earth rotates, and the Earth's rotation is gradually slowing due to tidal friction, an irreversible process. The water flows downhill. The pendulum would eventually stop without a driving weight or spring, because friction converts its energy into heat. Entropy increases. Even an atomic clock, precise as it is, requires energy to operate, and that energy eventually dissipates. Every clock, at some deep level, is an entropy machine. It marks the passage of time, because time's passage is entropy increasing. Now, Boltzmann's insight raises a question that's so deep it can keep you up at night, which I realize is the opposite of what we're going for here. So let's approach it gently. If the arrow of time comes from the universe starting in a low entropy state, then why did it start that way? Why was the early universe so ordered? Because the Big Bang, about 13.8 billion years ago, produced a universe that was incredibly hot, incredibly dense, and incredibly smooth, almost perfectly uniform in density. And that uniformity, counterintuitively, is a state of very low gravitational entropy. When matter is spread out evenly, gravity hasn't had a chance to do its thing yet, to clump matter together into stars, galaxies, black holes. All of that clumping is entropy increasing. The gravitational story of the universe is a story of entropy growing. So the arrow of time points from the Big Bang toward the future, because entropy has been increasing ever since that initial, improbable, low entropy beginning. The physicist Roger Penrose has called this the past hypothesis, the idea that the initial conditions of the universe were special, were low entropy, and that this is what gives time its direction. And here's what's humbling. We don't really know why the initial conditions were like that. It might be the deepest unsolved problem in physics. But let's come back down to Earth for a moment, because there's a beautiful practical dimension to all of this. The second law of thermodynamics, entropy always increases in a closed system, isn't just an abstract principle. It's the reason every engine, every power plant, every refrigerator, every living cell works the way it does. It sets absolute limits on efficiency. It tells you that perpetual motion machines are impossible. It explains why you have to pay your electricity bill. Every time you charge your phone, you're fighting entropy locally by pumping energy in. But globally, the total entropy of the universe goes up because the power plant that generated that electricity produced waste heat. You can create local order. Your body does it every second, assembling complex proteins from simpler molecules, but only by exporting disorder elsewhere. Life itself is a temporary, local decrease in entropy, sustained by a constant flow of energy from the sun, which is itself burning through its nuclear fuel irreversibly, its entropy climbing and climbing. And this brings us to something that I think is genuinely profound about the relationship between time and human experience. Because when you think about memory, about why we remember the past but not the future, that too is an entropy story. Your brain forms memories by creating ordered structures, specific neural connections, and that process requires energy and increases entropy in the surrounding environment. Memories are records of lower entropy states. You remember yesterday because yesterday the universe had lower entropy than today. You can't remember tomorrow because tomorrow hasn't happened yet. Its entropy hasn't been established. The psychological arrow of time, the thermodynamic arrow of time, and the cosmological arrow of time all point in the same direction, and as far as we can tell, they're all connected. So here we are. We started with Egyptian priests watching shadows creep across stone, and we've arrived at the statistical mechanics of the universe's initial conditions. And the thread connecting all of it is this relentless human drive to understand time more precisely, more deeply. But we're not done yet, because in the 20th century, the quest for precision in timekeeping took another extraordinary leap. One that would redefine what a second actually is and give us clocks so accurate that they could detect the curvature of space-time right here on the surface of the Earth. And that story begins with a curious property of atoms that scientists had been puzzling over since the early 1900s. See, when you heat up a gas, say hydrogen, and look at the light it gives off through a prism, you don't get a smooth rainbow. You get specific, distinct lines of color, sharp, precise frequencies, and by the 1920s, quantum mechanics had explained why. Electrons in an atom can only exist at certain energy levels, like steps on a staircase, not a ramp, a staircase. When an electron jumps from a higher step to a lower one, it emits a photon of light at a very specific frequency. And that frequency is determined by the energy difference between those two steps. Every atom of the same element has the same staircase. Every cesium atom in the universe, for instance, has exactly the same set of energy levels. Not approximately the same. Exactly the same. And that's a remarkable thing if you think about it, because it means that the frequency of light emitted by a particular atomic transition is a natural constant. It doesn't depend on where you are, or when you are, or who's measuring it. It's baked into the physics of the atom itself. And if you're in the business of defining a unit of time, if you want to say what a second really is, in a way that doesn't depend on the Earth's wobbly rotation or the slightly irregular orbit around the sun, well, atoms give you something to anchor to. The person who first seriously proposed using atomic transitions as a time standard was Isidore Rabi, a physicist at Columbia University. Rabi had won the Nobel Prize in 1944 for developing a technique called magnetic resonance, the same basic idea that would eventually give us MRI machines in hospitals. What Rabi figured out was a way to measure the resonant frequencies of atoms with extraordinary precision. You could expose atoms to microwave radiation and tune the frequency until the atoms responded, until they absorbed the energy and flipped between quantum states. When you hit the right frequency, you'd see a sharp signal, a peak. And that peak was incredibly narrow and stable, which meant you could use it as a reference, like a tuning fork for time. Rabi suggested this idea in a talk in 1945, and within a few years, the National Bureau of Standards, that's the old name for NIST, the National Institute of Standards and Technology, started building the first atomic clocks. The early ones used ammonia molecules, and they weren't actually more accurate than the best quartz crystal clocks of the day. But the concept was proven. And then, in the early 1950s, a British physicist named Louis Essen, working at the National Physical Laboratory in Teddington, outside London, built the first practical cesium beam atomic clock. Essen and his colleague Jack Perry got it running in 1955, and it was a revelation. This clock could keep time to about 1 second in 300 years, which might not sound mind-blowing compared to what came later. But remember, the best mechanical clocks of the era drifted by seconds per day. Quartz clocks drifted by milliseconds, and here was a device that essentially wouldn't lose a second in a human lifetime. Here's how a cesium clock works, at least in broad strokes. You start with a beam of cesium atoms, cesium-133 specifically. These atoms are heated in an oven until they vaporize, and then they stream out through a narrow slit as a beam. Now, cesium atoms have a property related to the spin of their outermost electron and the spin of their nucleus, and these spins can be aligned in two slightly different configurations. Two hyperfine energy levels. The atoms in the beam are a mix of both states. You pass them through a magnetic field that sorts them, deflecting atoms in one state away from the beam, and letting atoms in the other state continue. Then, the remaining atoms pass through a cavity where they're exposed to microwave radiation. If the frequency of those microwaves is exactly right, exactly matching the energy difference between the two hyperfine states, the atoms will flip from one state to the other. They absorb the microwave photon and transition. After the cavity, another magnetic field sorts the atoms again, and a detector counts how many atoms successfully made the transition. You tune the microwave frequency until you get the maximum number of transitions, the peak signal. And when you're at that peak, you know your microwave oscillator is running at exactly the right frequency. You lock it there, and now you have a clock. The magic number, the one that would eventually redefine the second itself, is 9,192,631,770. That's the number of oscillations of the microwave radiation corresponding to the cesium-133 hyperfine transition. In 1967, the General Conference on Weights and Measures, the international body that governs the metric system, officially redefined the second. No longer was it 1/86,400th of a mean solar day. Instead, a second was defined as the duration of exactly that many oscillations of cesium radiation. Think about what that means. For thousands of years, the second had been defined by the Earth, by its rotation, by its orbit. And now, suddenly, the second was defined by the behavior of an atom. The Earth was fired from its job as the official timekeeper of civilization. And here's the thing. The Earth deserved to be fired, because the Earth is not a great clock. Its rotation is gradually slowing down, mostly because of tidal friction from the moon. The days are getting longer by about 2 milliseconds per century. There are also irregular fluctuations. The Earth speeds up and slows down unpredictably due to shifts in its molten core, changes in atmospheric circulation, earthquakes redistributing mass. The astronomical second, defined by the Earth's motion, was a moving target. The atomic second is not. It's the same everywhere, for every cesium atom, forever. Or at least as far as we can tell. Now, once you have clocks this precise, something wonderful and slightly eerie starts to happen. You can actually measure effects that Einstein predicted, but that no one could directly observe with cruder instruments. Remember the Hoffel-Keating experiment from 1971, flying atomic clocks around the world on commercial jets? That confirmed time dilation, but the clocks they used were accurate to maybe a few nanoseconds. As atomic clocks got better, and they got much, much better, the experiments you could do became almost absurdly sensitive. By the 21st century, optical atomic clocks had arrived. These work on the same basic principle as cesium clocks, but instead of using microwave transitions, they use transitions in the visible or ultraviolet range, frequencies hundreds of thousands of times higher. Higher frequency means more oscillations per second, which means finer resolution, which means better accuracy. Modern optical clocks using strontium or ytterbium atoms trapped in lattices of laser light can keep time to about 1 second in 15 billion years. That's roughly the age of the universe. If you'd started one of these clocks at the Big Bang, it still wouldn't have lost a second by now. And with that kind of precision, you can do something that would have seemed like science fiction even a few decades ago. You can detect gravitational time dilation over a height difference of a single centimeter. Einstein's general relativity tells us that time runs slightly slower in stronger gravitational fields, closer to a massive object. We talked about this with GPS, where satellites experience weaker gravity than the ground, and their clocks run faster by about 45 microseconds per day. But with optical clocks, you can see this effect on a laboratory bench. In 2010, researchers at NIST, led by a physicist named James Chinwen Cho, took 2 optical clocks and placed one just 33 centimeters higher than the other, about a foot, and measured that the lower clock ran slower. The difference was tiny, on the order of parts in 10 to the 17th, but it was real and it was measurable. Time literally passes at a different rate for your head than for your feet. You're aging faster at the top of your body than at the bottom. Not by much. Over an 80-year lifetime, the difference between your head and your feet would amount to maybe a few billionths of a second. But it's real. It's not a metaphor or an approximation. Space-time is genuinely curved by the Earth's mass, and these clocks can feel it. This opens up applications that are still being explored. One of the most intriguing is using atomic clocks as gravity sensors. If you have a network of ultra-precise clocks at different locations, the differences in their tick rates tell you about the gravitational field, which tells you about the distribution of mass underground. You could potentially detect changes in underground water tables or magma movement beneath volcanoes or even shifts in ice sheets, just by watching how clocks at different locations drift relative to each other. It's called relativistic geodesy, and it's still in its early stages, but the idea is extraordinary. Clocks that were originally built to keep time are now being used to map the shape of space-time itself. And this precision has created a new kind of problem for timekeeping, one that echoes, in a funny way, the old tension between solar time and clock time that the railways had to sort out in the 1800s. Because we now have two kinds of time running in parallel. There's International Atomic Time, or TAI, from the French Temps Atomique International, which is maintained by a network of about 400 atomic clocks in laboratories around the world, all contributing to a weighted average. TAI is relentlessly uniform. It ticks at exactly the rate defined by the cesium standard, and it never adjusts, never wavers. And then there's Coordinated Universal Time, UTC, which is the time standard that the world actually uses. The time on your phone, the time that air traffic control uses, the time that time stamps your emails. UTC is based on TAI, but with a crucial modification: leap seconds. Because the Earth's rotation is slowing down, astronomical time gradually falls behind atomic time. The days are getting longer, remember? So every now and then, roughly every year and a half on average, though the interval is irregular, the International Earth Rotation and Reference System Service adds a leap second to UTC. At the end of some particular day, usually June 30th or December 31st, the clock reads 23 hours, 59 minutes, 60 seconds before ticking over to midnight. An extra second inserted to keep UTC within 9/10 of a second of the Earth's actual rotation. And this drives some people absolutely crazy. Not in a philosophical sense, in a very practical, engineering sense. Because modern computer systems, telecommunications networks, financial trading platforms, they all depend on precise timestamps, and inserting an extra second into the timeline causes real problems. Software crashes. Systems that expect 60 seconds in a minute suddenly encounter 61 and don't know what to do. In 2012, a leap second caused outages at Reddit, Mozilla, LinkedIn, and several airline booking systems. The fundamental issue is that leap seconds are unpredictable. You can't schedule them years in advance because the Earth's rotation is irregular. And they create a discontinuity in what's supposed to be a smooth, continuous time signal. So there's been a long-running debate about whether to abolish leap seconds entirely. Just let UTC run on pure atomic time, and accept that, over centuries, clock time will gradually drift away from solar time. The sun would reach its highest point a little later each year, and in maybe 1,000 years, noon on the clock wouldn't correspond to noon in the sky. But honestly, for most practical purposes, that wouldn't matter. We already live by clock time, not sun time. Your phone doesn't tell you when the sun is overhead. It tells you what the Coordinated Global Time Standard says. In November 2022, the General Conference on Weights and Measures voted to abolish leap seconds by 2035. The details are still being worked out: how to handle the accumulated difference, what tolerance to allow. But the direction is clear. Atomic time is winning. The atoms have replaced the stars. And yet, even as we settle that question, the frontier of timekeeping keeps pushing forward. Because cesium clocks, as extraordinary as they are no longer the most precise clocks we can build. Those optical lattice clocks I mentioned, the ones accurate to 1 second in 15 billion years, they're so much better than cesium, that there's serious discussion about redefining the second again, moving from a microwave transition to an optical one. It would be the most precise measurement standard humanity has ever established for anything, and the candidates being considered, the atoms that might anchor the next definition of a second, include strontium, ytterbium, and aluminum ions, each trapped and cooled to near absolute zero, their quantum states probed by lasers of extraordinary stability. The committees are meeting, the comparisons are being made, and sometime in the next decade or so, the second will likely get a new definition, one that's perhaps 100 times more precise than what we have now. But precision at this level starts to bump up against questions that aren't really engineering questions anymore. They're physics questions, fundamental ones. Because if your clock is sensitive enough to detect the curvature of space-time over a centimeter, then the very concept of a single, universal time becomes something you have to question. Really question. Not in a hand-wavy philosophical way, but in a hard, precise, physical way. Because here's what those clocks are telling us. There is no single now. There never was. And I know that sounds like the kind of thing someone says at a party to sound deep. But this is different. This is measurable. This is what the instruments are screaming at us. When Junye's group at NIST took one of those optical lattice clocks and showed that raising it by 33 centimeters, about a foot, made it tick measurably faster, they weren't just demonstrating a cool trick. They were showing that the question, "What time is it?" doesn't have one answer. It has a different answer at the height of your head than it does at the height of your feet. And the difference is real. It's not an error. It's not an artifact. It's the actual structure of the universe making itself known. Now, for most of human history, this didn't matter. It couldn't matter. Our clocks weren't good enough to see it. A sundial doesn't care about relativistic frame dragging. A pendulum clock doesn't notice gravitational redshift. Even the best quartz oscillators are far too crude to pick up on these effects at human scales. But now, we've built instruments that can. And once you can see something, you can't unsee it. The universe has handed us a receipt, and it says, time is local. Let's sit with that for a moment. Think about what simultaneity means. You're lying there right now, and somewhere across the room, there's a wall, and you'd probably say that the clock on your nightstand and an imaginary clock on that far wall are experiencing the same now, the same moment. But Einstein showed, back in 1905, and we talked about this, that simultaneity is relative. Two events that are simultaneous for one observer aren't necessarily simultaneous for another observer moving at a different velocity. That was the lesson of special relativity. And then general relativity added another layer. Even if you're not moving relative to each other, if you're at different heights in a gravitational field, your clocks run at different rates. Not because the clocks are broken, but because time itself flows differently. For a long time, this was a theoretical point. A beautiful, verified, but largely academic point. Haffel and Keating flew atomic clocks around the world and measured the difference. GPS satellites correct for it every day. But those are big effects. Satellites orbiting at 20,000 kilometers, jets moving at hundreds of meters per second. The new clocks are seeing these effects across the height of a kitchen table, and that changes the conversation. Here's why. If you want to define a universal time, a single synchronized now that everyone on Earth agrees on, you need to be able to compare clocks. You need to say, this clock and that clock are ticking at the same rate, and they agree on what time it is. But if the clocks are precise enough to detect that they're ticking at different rates because one is a few centimeters higher than the other in Earth's gravitational field, then there is no single rate. There's no master clock that's right. Every location in the universe has its own proper time, its own flow, and the best you can do is pick one and call it the reference. Which is, honestly, what we already do. International Atomic Time, TAI, is computed by averaging the output of about 450 atomic clocks in 80 laboratories around the world. But, and this is the key part, each of those clocks has to have its tick rate corrected for its altitude. A clock in Boulder, Colorado, which sits about 1,600 meters above sea level, ticks faster than a clock at sea level in Paris. Not by much, about 1 part in 10 to the 13th. But it's there, and if you don't correct for it, the whole system drifts. So the Bureau International des Poids et Mesures, the BIPM in Paris, takes all these clock readings and mathematically adjusts them to what they would read if they were all at the geoid, the hypothetical sea-level surface of the Earth. They're computing time on a surface that doesn't physically exist, a mathematical fiction that lets us pretend there's a universal now. And that works. It works beautifully, actually. It's one of the great quiet achievements of modern metrology. But the better the clocks get, the harder this becomes, because the geoid itself isn't perfectly known. The Earth's gravitational field is lumpy. It's affected by mountain ranges, ocean trenches, the density of rock underground, even the movement of magma in the mantle. Satellites like GRACE and GOSI have mapped the geoid with extraordinary precision, but there are limits. And if your clock can detect a height difference of a centimeter, then you need to know the geoid to a centimeter, which we don't. Not everywhere. So the clocks are now more precise than our knowledge of the gravitational field they're sitting in. The instruments have outrun the map. This is where it gets really interesting, because it flips the problem on its head. Instead of using our knowledge of gravity to correct the clocks, we can use the clocks to measure gravity. That's relativistic geodesy, the idea that an optical clock is actually a gravity sensor. You put one clock at the top of a mountain and one at the bottom, you compare their tick rates via a fiber optic link, and the difference tells you the gravitational potential difference between those 2 points, more precisely than any gravimeter, more precisely than any satellite. You're using Einstein's general relativity not as a nuisance to be corrected for, but as a measurement tool. The theory that made timekeeping harder is now making Earth science better. Teams in Europe have already demonstrated this. In 2020, researchers connected optical clocks in France, Germany, and the UK via fiber optic links spanning hundreds of kilometers and compared their tick rates. The results were consistent with the known gravitational potential differences between the sites, and the precision was approaching the level where you could detect changes in the geoid caused by things like tidal loading, the slight deformation of the Earth's crust as ocean tides push water around. Imagine that. Clocks so precise that the sloshing of the ocean slightly changes how fast they tick, and they can feel it. But let's push further. Let's go past the practical and into the truly fundamental, because that's where the night gets deep and the questions get strange. We've been talking about time as something that flows, faster here, slower there, but always flowing, always ticking, always moving forward. But is it? Is time actually a fundamental feature of the universe? Or is it something that emerges from deeper processes, the way temperature emerges from the motion of molecules? This is one of the biggest open questions in physics. And it's not idle speculation. It comes directly from the tension between our two best theories of reality. General relativity, Einstein's masterwork, treats time as a smooth, continuous dimension woven together with space into space-time. It curves, it stretches, it bends around massive objects, but it's always there, always smooth, always well-defined. Quantum mechanics, on the other hand, the theory that governs atoms and subatomic particles, and, not coincidentally, the theory that makes our atomic clocks work, treats time very differently. In quantum mechanics, time isn't an observable the way position or momentum is. It's a parameter, a background label. The equation tells you how a quantum state evolves in time, but it doesn't treat time as something the quantum system itself experiences. It's more like a stage than an actor. And when you try to combine these two theories, when you try to write down a quantum theory of gravity, time becomes deeply problematic. The most famous attempt, the Wheeler-DeWitt equation, written down by John Wheeler and Bryce DeWitt in the 1960s, describes the quantum state of the entire universe. And here's the kicker. It has no time variable. The equation is timeless. It describes a static quantum state, which seems insane, because obviously things change. You're lying there, your heart is beating, the earth is spinning, the universe is expanding. How can the fundamental equation of everything be timeless? One answer, and this is the one that Carlo Rovelli and others have championed, is that time is relational. It doesn't exist as an independent thing flowing in the background. What exists are correlations between physical systems. When you say the train arrives at noon, what you really mean is the train arrives when the clock hands point to 12. You're not comparing the train to some absolute time. You're comparing one physical system, the train, to another physical system, the clock. Time is just the word we use for certain kinds of correlations between things that change. And if that's true, then at the most fundamental level, there might not be a thing called time at all. There might just be change and relationships between changes, and the rest is a story we tell ourselves because our brains evolved to navigate a world where tracking sequences of events kept us alive. Now you might be thinking, okay, but that's philosophy. Where's the physics? And that's fair. But here's where it connects back to real measurable things. If time is emergent rather than fundamental, then there should be a scale at which the smooth, flowing time of our everyday experience breaks down, and there's a candidate for that scale. It's called the Planck time. It's about 5.4 times 10 to the negative 44 seconds. That's a decimal point, followed by 43 zeros, and then a 5. It's incomprehensibly small. The age of the entire universe is only about 4.3 times 10 to the 17th seconds. The Planck time is smaller than a second by a factor that dwarfs the number of seconds in the history of the cosmos. At the Planck scale, our current theories predict that the smooth fabric of space-time should become turbulent, foamy, uncertain. Quantum fluctuations should make the very geometry of space and time jitter and roil. Some physicists call it space-time foam, a term Wheeler coined actually, the same Wheeler from the Wheeler-DeWitt equation. He imagined that if you could zoom in far enough, the smooth space-time of general relativity would dissolve into a seething quantum froth where the concepts of before and after lose their meaning. We can't probe the Planck scale directly, not even close. The energies required would be far beyond anything we can produce. You'd need a particle accelerator the size of a galaxy. But there are indirect approaches. Some theories predict that Planck-scale graininess of time might leave subtle signatures in the light from distant astronomical objects. Gamma-ray bursts billions of light-years away, for instance. If time has a minimum grain size, then photons of different energies traveling across the universe for billions of years might arrive at very slightly different times, even if they were emitted simultaneously. Telescopes like the Fermi Gamma-ray Space Telescope have looked for this effect. So far, the results have been null. No evidence of Planck-scale dispersion, which either means the effect isn't there, or it's smaller than our current instruments can detect, or our theories about what to look for are wrong. But the search continues, and meanwhile, the clocks keep getting better. There's a beautiful irony here, if you think about it. We started this whole journey with humans noticing that shadows move across the ground, that the sun rises and sets, that seasons come and go. Time, for most of human history, was the most obvious thing in the world. It was the thing you could always count on. The sun comes up, the sun goes down, and another day has passed. And now, after thousands of years of building better and better clocks, from sundials to water clocks, to pendulums, to quartz to cesium, to optical lattices, we've arrived at a place where the very thing we were trying to measure has started to dissolve under our gaze. The closer we look at time, the less solid it seems. And yet the clocks still tick. The GPS satellites still correct for relativity and deliver your position to within a meter. The trains still run on schedules. Your phone still knows what time it is. The practical infrastructure of time, the thing that Harrison fought for, that Fleming organized, that Essen pinned to a cesium atom, all of that still works. It works because at the scales of human life, time is robust. It flows forward, it's measurable, it's consistent, enough to build civilizations on. The weirdness lives at the extremes, at the Planck scale below, at the cosmological scale above, at the bleeding edge of precision where centimeters matter. So where does that leave us? With a question that I think is genuinely one of the most profound questions humans have ever asked, and it's a question that started with a stick in the sand casting a shadow, and it's led us all the way to the edge of everything we think we know. What is time? Is it a river that carries us? Is it a dimension we move through, the way we move through space? Is it an illusion, a trick of thermodynamics, a story our brains tell themselves so that consciousness makes sense? Or is it something else entirely? Something we don't have the framework for yet? Something that will require a revolution in physics as profound as the one Einstein triggered in 1905? Here's what I find so moving about that question. It's not just a physics question. It never was. Every culture that has ever existed has grappled with it. The Egyptians who planted that first shadow stick in the ground at Karnak, they weren't just trying to organize their day. They were trying to understand their place in the cosmos. When does the flood come? When do the stars return to their positions? How long do we have? Those are practical questions, sure, but underneath them is something deeper, something existential. Time is the medium in which we live and die, and the desire to measure it has always been tangled up with the desire to understand it, and the desire to understand it has always been tangled up with the desire to somehow master it, to hold it, to not lose it. And the beautiful thing, the thing that I keep coming back to, is that every single step in this story was driven by a practical need. Nobody sat down and said, let's figure out the nature of time. They said, we need to know when to plant the crops. They said, we need to know when to pray. They said, we need to stop losing ships. They said, we need the trains to stop crashing into each other. They said, we need to land this airplane in fog. They said, we need this GPS signal to be accurate. And each time, the solution to the practical problem peeled back another layer of the mystery. Sundials revealed that the Earth's orbit isn't perfectly circular. Pendulum clocks revealed that gravity varies from place to place. Marine chronometers revealed that longitude is a problem of time, not space. Railway schedules revealed that local solar time is a fiction we can't afford. Atomic clocks revealed that the second itself needed a new definition. And optical lattice clocks, those impossibly precise instruments that can detect the difference in time's flow over 33 centimeters of height, they're revealing that space-time itself is a landscape, not a backdrop. That the geometry of the universe is written in the ticking of clocks, so the practical need drives the technology. The technology reveals the physics reshapes our understanding, and the understanding raises new questions that nobody anticipated. It's a spiral, and it's been spiraling for 5,000 years, and it's still going. Let me tell you where the spiral is pointing right now, because it's genuinely fascinating, and it's a nice place to let your thoughts drift as you settle in. One of the most active frontiers in physics, and this connects directly to the clocks we've been talking about, is the search for a theory of quantum gravity. We talked about how general relativity and quantum mechanics don't play well together. General relativity says space-time is smooth, dynamic, curved by mass and energy. Quantum mechanics says everything at small scales is quantized, probabilistic, jumpy. Time in general relativity is woven into the fabric of the universe. Time in quantum mechanics is just a label, a background parameter, something the equations refer to but don't explain. These two descriptions of reality are both extraordinarily successful in their own domains, and they flatly contradict each other about what time is. Now there are several approaches to resolving this. String theory is one. It posits extra dimensions and tiny vibrating strings, and it has a lot of mathematical elegance, but it's proven very difficult to test experimentally. Loop quantum gravity is another. It tries to quantize space-time itself, breaking it into discrete chunks. Little loops of gravitational field woven together into what physicists call a spin foam. In loop quantum gravity, space isn't continuous. It comes in smallest possible volumes on the order of the Planck length cubed. And time, similarly, might come in smallest possible durations, ticks of a cosmic clock at the Planck scale, about 10 to the minus 43 seconds. Below that, the concept of before and after might not even apply. And then there's the approach that Carlo Rovelli has been championing, which we touched on earlier. The idea that time might not be fundamental at all. That what we call time is an emergent phenomenon, something that arises from the relationships between physical systems, from the flow of information, from the increase of entropy. In this view, the universe at its most fundamental level is timeless. The equations that describe it don't need a time variable. What we experience as the passage of time is a macroscopic effect, like temperature. Individual molecules don't have a temperature. Temperature is a property of large collections of molecules. Similarly, individual quantum events might not have a time. Time might be a property of large collections of quantum events, a statistical phenomenon that emerges when you zoom out far enough. Think about what that means. If Ravellian physicists like him are right, then time, this thing that feels so fundamental, so undeniable, so intimately woven into every moment of your experience, is not a feature of the universe. It's a feature of your perspective on the universe. It's real in the same way that temperature is real, or that a wave is real. You can surf on a wave. A wave can knock you down. But a wave isn't a thing. It's a pattern, a behavior of water molecules. Time might be like that. A pattern, a behavior of something deeper. Now, I want to be honest with you. Nobody knows if this is true. This is frontier physics, and frontier physics is messy. There are brilliant people who think time is fundamental, and brilliant people who think it's emergent, and brilliant people who think the question itself is malformed. We don't have the experimental tools yet to distinguish between these possibilities. The Planck scale is so unimaginably small that no particle accelerator we can build, nothing even close to what we can build, can probe it directly. That's why those Fermi telescope observations we mentioned were so interesting. They were trying to catch indirect evidence of Planck scale structure by watching how gamma rays from distant explosions travel across billions of light years of space. And they found nothing. Space-time looked perfectly smooth, all the way down to the limits of their measurement, which doesn't prove that space-time is smooth at the Planck scale. It just means that if there's graininess, it's subtler than the simplest models predicted. But here's where the clocks come back into the story. And this is what I find so poetic. Those optical lattice clocks, the ones that Junye and his colleagues are building at Gila in Boulder, the ones that lose less than a second over the age of the universe, they might actually become tools for probing these questions. Not directly, not at the Planck scale, but by measuring gravitational effects with such extraordinary precision that they can test predictions of general relativity in regimes where quantum gravity effects might start to whisper. If you can measure the gravitational redshift, the slowing of time in a gravitational field, with enough precision, you might detect tiny deviations from what Einstein's equations predict. Deviations that could hint at the quantum structure of space-time. It's the same pattern we've seen throughout this entire story. Better clocks leading to deeper physics. Harrison's chronometer solved longitude. Essen's cesium clock redefined the second. And maybe, just maybe, the optical lattice clocks of the 21st century will help us understand whether time is woven into the foundations of reality, or whether it's something that emerges, like a melody emerges from individual notes. And you know, there's something comforting about that uncertainty. I mean it. There's something deeply human about lying here in the dark, thinking about time, and realizing that after 5,000 years of trying, we still don't fully understand it. The Egyptians didn't understand it. Aristotle didn't understand it. Newton thought he did, but he was wrong, or at least incomplete. Einstein got closer than anyone, but even he knew his theory was incomplete, that it would eventually need to be reconciled with quantum mechanics. And here we are, in the 21st century, with clocks that are accurate to 18 decimal places, and we still can't answer the simplest question a child might ask. What is time? But we've learned so much along the way. We've learned that time is not absolute. It bends and stretches depending on how fast you're moving and how deep you are in a gravitational field. We've learned that it has a direction, and that direction is tied to entropy, to the thermodynamic arrow that points from order to disorder, from the low-entropy Big Bang toward the high-entropy future. We've learned that our experience of time, the feeling that the past is fixed and the future is open, that now is special, that moments flow. is not written into the laws of physics. The equations work just as well backward as forward. The now that feels so vivid to you, this present moment, has no special status in relativity. It's yours. It's local. It's personal. And we've learned that measuring time with ever greater precision is one of the most powerful things humans have ever done. It's given us navigation, communication, global coordination, satellite networks, the internet, the ability to synchronize the actions of 8 billion people across a spinning planet hurtling through space at 100,000 kilometers an hour. All of that rests on clocks, on the accumulated ingenuity of every person we've talked about tonight. The Egyptian priest watching the shadow, Ctesibius tinkering with his water clock in Alexandria, the anonymous medieval monks who built the first mechanical escapements, Galileo watching that chandelier swing in the cathedral at Pisa, Huygens building his pendulum clock in The Hague, Harrison spending decades of his life on a problem everyone said was impossible, Fleming standing in a railway station in Ireland after missing his train, Essen and Perry counting the vibrations of cesium atoms in a laboratory in Teddington. Every one of them was trying to solve a practical problem. And every one of them, whether they knew it or not, was contributing to humanity's long, slow, magnificent attempt to understand the deepest feature of our existence. So here you are, lying in the dark, and time is passing. Or at least, it feels like it is. Your body's circadian rhythms, those ancient biological clocks tuned by millions of years of evolution to the 24-hour cycle of light and dark, are doing their work right now. Melatonin is flowing. Your core temperature is dropping. Your brain is beginning to shift into the slower wave patterns of sleep. And in a way, your body is the oldest clock of all. Older than sundials, older than language, older than civilization. Life itself learned to keep time long before humans ever thought to try. And as you drift off, here's one last thought to carry with you. Time might be the most generous mystery there is. Because unlike so many of the big questions, what's the universe made of? How did life begin? Are we alone? Time is something you experience directly, constantly, intimately. You don't need a telescope or a particle accelerator. You just need to lie still and notice. Notice the breath going in and out. Notice the thoughts rising and falling. Notice the gentle pull of sleep. That's time. Whatever it is, whether it's fundamental or emergent, whether it's a dimension or an illusion, whether it flows like a river or sits still while we move through it, you're in it. You're made of it. Every memory you have is a record of it. Every heartbeat is a clock ticking inside you. 5,000 years of human ingenuity, from a stick in the sand to an optical lattice trapping strontium atoms, and the most sophisticated instrument for experiencing time is still the one you were born with. Your mind, your consciousness. This quiet awareness, right now, of one moment becoming the next. So let it become the next, and the next. Let the moments flow, or let them be still, whichever feels right. The clocks will keep ticking. The cesium atoms will keep vibrating. 9,192,631,770 times, and that will be 1 second, and then another, and then another. And you don't need to count any of them. They'll be there in the morning. Time, whatever it is, will still be here. And so will you. Good night.